All right, sorry.
Okay, so our next talk's on CacheIR, and we have two speakers. So Matthew and Iain are going to give a talk.
Yeah. All right, I promise I'll go fast. So, this talk we're going to talk a little bit about inline caching in a JavaScript engine, a little bit about how it tends to be presented, how it actually sort of works in one specific engine, and why we built an intermediate representation for our inline caches, and then some cool advantages that that brings. So, inline caches tend to be talked about pretty simply. So there's a model that, when you are teaching an undergrad course or something that you're going to talk about, where it's like, well, in the code itself, you'll put, often it's taught in the context of small talk. So for example, you'll have a method send, and you'll say, I have a receiver, and if I see an object with the same receiver type, again, I can go and I will use the discovered target method, and we'll save that right there, and we'll use it over and over again. And then there's the follow-on work, which is, hey, some things are polymorphic, so why don't we store multiple in there? The problem with this presentation is that it tends to limit people's view on what actually you can use inline caching for and how powerful of a technique it can be. And so one of the reasons I wanted us to write this paper was to just try to actually make that clear, that inline caching is a super powerful technique and that we can do a lot more with it than maybe is being taught. So, inline caches aren't really just caches. And even if you go back to the paper that introduced this from Deutsch and Schiffman, they kind of allude to it, but it's not being made very clear. So we adopt the approach inside of SpiderMonkey that essentially any behavior that can be specialized based on something about the input types can get an inline cache. And so this includes things like property access. This includes things like calls. This includes things like arithmetic operations. And in calls, we can even do things like a simple form of inlining. Now, we're going to talk a little bit about the inline cache architecture inside of SpiderMonkey. So SpiderMonkey, like a lot of language VMs, compiles source text into bytecode. Our bytecode, any bytecode that is eligible for an inline cache, will start in this unlinked state where you have a pointer to a fallback stub. So the fallback stub is written in C++, and its job is to always be able to provide an answer. It's always able to resolve the input. When you do that, though, we can attach a stub. So you've seen, for example, the addition of an integer to an integer. Well, this is a point at which you would say, let's add a stub. So the stubs form a linked list, and so we'll have stub 1, stub 2, stub 3, stub 4, and each of these will point to native code that actually implements the operation. And the chain will always end in the fallback stub, so you can always handle every single case. In SpiderMonkey, we create stubs using CacheIR. So CacheIR is a simple typed bytecode specialized for the case of inline caches. It's linear. We only have two control flow operations. We have guards, where we're asserting some property is true, and if it's not true, we just give up and jump to the next stub. And we have return. So you have succeeded in running this inline cache. Let's return the value and get out. Immediates are stored inside of stub fields, which you can sort of think of as constant pools if you've used a language with constant pools. And so in this example, we have guard to object, which you can't see my cursor. So you have guard to object. This is converting an input, which could be any type, and saying if it is an object, then return a new operand ID of type object. It's guard type shape, so make sure that that object has a specified known shape. If it does, then we're going to load a fixed slot result, and we're going to say get the result out of a particular slot in the object and put it into the result register. And now, once that happens, we're done. So we return. One of the things to note here is that all of the dynamic information is stored separately because we want to be able to actually recycle these stubs. There's lots and lots of them in an actual production compiler. So we don't want to be compiling a new one for every instance. So we generate these stubs in the fallback cache path, and the model kind of looks like this. So we generate CacheIR, and we hand it off and say, for the baseline compiler, we'll go and we'll check a pre-existing cache. The nice thing about CacheIR is that it acts as a perfect cache key to say whether or not we can recycle the native code. Because we load everything out of the stub fields or the constant pool, the native code will work for multiple stubs with different shapes. Our Ion CacheIR compiler works a little bit differently because it interacts with our register allocator. So currently we don't do any sharing for Ion cache ICs, but we're talking about it. So why add an intermediate representation? Well, we're compiler people, and intermediate representations are neat. They're lots of fun. Why wouldn't we? Really, though, I mean, it's a lot of the traditional reasons why you actually add an intermediate representation. So it's separation of concerns, separating the ability to reason about your inline caches from how they're actually implemented and executed. The other advantage here is that it provides a shared representation throughout the engine. This deduplicates effort. It replaces a system where we could get into situations where we would have inline caches that worked only for our baseline compiler and not for our top-tier compiler. And yeah, I already mentioned the baseline code sharing made robust using the inline cache representation as the key. At this point, I will hand it off to Iain.
Hi, so I'm going to talk a little bit about Warp Builder, which is the JIT that we built on top of CacheIR. So after we'd used CacheIR to unify how we implement baseline ICs and Ion ICs, we turned our attention to our optimizing JIT, and the result was Warp Builder. It is the new-ish front end. We actually shipped it a few years ago, but we're just talking about this now, for Ion, which is our highest tier. And while querying inline caches to get information for your optimizing compiler is nothing new, in this case, we really leaned into it. And so CacheIR allows us to treat the process of looking at what our ICs have done as a lowering step rather than as a querying step. So as an example of how this works in practice, if we have some very simple source code that's just a function that's adding two numbers together, this will have some bytecode. It gets the arguments, it adds them, it returns them. This is a stack-based machine. And then we have CacheIR for this that will guard each of these values, add them together, and then return the result. And now what Warp Builder will see is it will start walking through the bytecode. It will see we get an argument, we get another argument, and then when it gets to the add, the important thing to realize is that Warp Builder actually knows absolutely nothing about addition. Instead, all it knows is, well, there's an IC for this, let me go check the ICs. And it will see, I have a monomorphic case where we have done a guard to an int and another guard to an int, and then added them together. And so it will take those guards and it will lower those to a fallible unbox, where in the generated top-tier code, we will say, we expect this to be a 32-bit integer. We will unbox it. If it isn't, then we will bail out and learn more and then recompile again later, potentially. And then we return back to the bytecode. We continue generating it. If the IC chain is polymorphic, then we just create an IC and Ion, and we get all the benefits of ICs there. And if the IC chain is empty, then we can just create an unconditional bailout, which allows us to do branch pruning of purportedly dead code that has never been reached before. So briefly comparing this to what it was replacing, we used to have Ion Builder, which you can see on Matt's shirt, and because this was back when we made posters for our projects. It was a dynamic type inference. It did a whole program analysis where we partitioned objects into groups and tracked properties per object. And it was all very, very clever, and you can go read the paper about it. But fundamentally, it was very big and complicated and brittle. And so the advantages of Warp Builder are, first of all, that it is a single source of truth. That it is a single place where every speculative optimization that we do is implemented in one place, where we say, if I have seen two integers, I know what to do. If I have seen a call to this particular built-in, I know what sort of code to generate there. And it exists in exactly one place rather than needing to look at your inline caches and then figure out what to do again based on that. This is good for correctness, it is good for simplicity, it is good for avoiding missed optimizations that are only performed in one tier. Compared to what came before, it involves much more local reasoning because all of the guard conditions are very local to what you're looking at rather than depending on state being maintained in the metadata across the engine. And it's much lower global overhead. We effectively get type specialization for free because we already want to have inline caches tracking this so that we can have the benefits of performance in baseline, and then when it comes time to have an optimizing compilation, the metadata that we're tracking is precisely the metadata that we already needed, and so we're not paying extra for that, where Ion Builder was. Lower tiers don't end up having to pay for collect data they don't use. That's great. One disadvantage is that this does end up with more guards and hot code. So this is very similar to what Maxime said. There are cases where you are trading off peak performance for warm-up, and what we found is that in practice, on the real web, trading a little bit of peak performance for a lot of warm-up advantages and stability and reduced memory consumption is a great trade-off, and we are very happy that we made it. So a few other cool things that we've done. Once you have CacheIR, we do this thing called trial inlining. So as I mentioned, we only actually lower things if the IC is monomorphic, and we want to have as many monomorphic ICs as possible. So you can have a case where you have a function that is being called in multiple places with different types. And if you just do if you just run this, then inside this function, we will have one IC chain that has two different ICs in it. And so if we didn't do any inlining, this would be polymorphic. To make it work, what we do is we start by having this version where we're doing two separate calls, and then partway through execution, we start doing our inlining. We make our tentative inlining decisions, and so we say, okay, in this case, I see that I have an IC with a single target, and I see that that target contains polymorphic ICs. We then create a separate private batch of ICs specific to that call site and rewrite the IR stub that was doing the call scripted to a call inlined. And because this is an IR, we just have to find places where we have a guard-specific function operation and a call scripted function operation, and then we can just clone the entire thing and replace the last instruction from call scripted to call inlined, and everything else works. So there may be different guards that we need depending on case, but that all gets optimized away and is orthogonal because we have a separate IR for this. And then when we execute this call site will only see a 32-bit integer addition, and this one will only see a string concatenation, and therefore we end up getting monomorphic ICs, which is pretty cool. So after we do trial inlining, we have private per call site ICs, and they're monomorphic. A couple of other fun tricks that I'll run through quickly. Again, because this is an IR, we can do a thing called stub folding, where if you have a bunch of stubs that have exactly the same IR, except they're guarding on a slightly different shape, then we can take that, recognize that mechanically, and smush it all down by just taking that code, replacing the guard shape operation with a guard multiple shapes operation, and changing nothing else. And so we only need to implement this small change, and we get this for anything that might be using shapes. Because it's an IR, it's very easy to hash it, and so we can do a bailout loop detection where we can guarantee that we are never recompiling without having learned something new about this and monomorphically move towards a steady state modulo GC pressure. We think that the ideas that we're presenting in this paper are more interesting than the empirical results, but the empirical results are actually also pretty good. So again, calling back a little bit to the previous presentation, there are a couple of benchmarks that are really popular in JavaScript land, and one of them is speedometer, and it's the good one. And so you can see that when we moved from Ion Builder to Warp Builder, we got an improvement on speedometer. And the other is Jetstream, and it's the bad one. And so when we moved there, we took a known hit because we didn't care. And since then, we have put some work in that has actually moved our score up. But the really interesting thing was that just moving from the let's get maximum performance at all, maximum top tier performance at the cost of everybody else design of Ion Builder to Warp Builder almost instantly gave us better performance on the benchmarks that we actually care about before we had even really put any optimization effort in. This is Spider Monkey poking its head out of the industry hole for, I guess, last time we did this was 2012. We're always happy to collaborate with people. We're hoping to do some more research opportunities, so we're working with some people at the University of Alberta on this paper. We have been collaborating with some people at Fastly on precompiling, or on doing this in a JIT-free environment using interpreted CacheIR. If you have any ideas, please come talk to us, and we're open for questions.
Okay, we have plenty of time for questions. You come up to the microphone.
I wanted to ask the reasoning for the empirical results. So like, does the subfolding or something specific to the WAP builder like contributing to the improvement? Like, is it possible to implement the same technique in Ion builder, or is that just easier in WAP builder? So I'm kind of curious why this.
Right. So a lot of the improvement was because Ion Builder had originally been designed to optimize Octane, which was like the precursor to Jetstream and even worse. And so it was a lot of very small code base, here's a very, very small hot loop. Can you make this as fast as possible? Whereas Speedometer is taking a bunch of actual real-world JavaScript frameworks and then doing sort of like, here's a basic app. And so because Ion Builder had a lot of, imposed a lot of overhead on colder code, as soon as you moved from something with a very hot profile to something with a flatter profile, those costs were no longer being hidden in code that never ran, and therefore the benefits of having good performance on everything rather than great performance on hot code and less good performance on colder code, that trade-off started to pay off in the direction of Warp Builder. It let us reduce memory consumption a lot because we had been tracking these big graphs of what every object could be pointing to and so on. And it let us get rid of a bunch of places where we had all of the baseline code needed to be tracking what types am I storing into objects to maintain that.
The hot and cold thing was like the layout problem. Like, do you place like hot code together, or is that just you mainly optimize the like hot path by introducing the new type of the inline cache?
So Warp, like we're a standard tiering JIT where the we only once code has gotten hot enough, then we will tier up to the top level.
Right.
So Warp Builder itself isn't necessarily going to improve cold code, but the fact that we're using Warp Builder rather than Ion Builder means that the colder code does not pay costs for Warp Builder, and therefore it ends up being faster, not because Warp Builder is doing anything, but because Warp Builder isn't requiring the cold code to track things. Does that answer your question? Sorry, I wasn't.
Yeah, it does. Thank you.
Cool. Just one more.
So I'm curious about what you said about reducing the warm-up start. So can you actually move it to an extreme and actually compile code ahead of time, or share code across other engines that are running simultaneously? And what's the impact on performance?
So we're currently we currently share our baseline ICs that have the same CacheIR sequence across an entire runtime. So basically, a tab, there will just sort of be one, like a huge fraction of all IC stubs are a basic get prop that says, check that this is an object, check the shape, and then load the value from a particular slot. And so we only actually have one copy of that code, or maybe a couple for technical reasons, that gets shared across an entire tab. We are looking at also collecting the list of those things and pre-compiling those and baking them into the binary, which would be a small improvement. We're not sure exactly what the scope of it is, because these are fairly fast to compile, but it does pay off. And yeah, we're working on moving more compilation earlier. This is a helpful way to have organized things to do that.
Okay, yeah. I was curious about the performance impact, but we'll talk in offline.
Okay. Sure, yeah, maybe ask me afterwards and I'll have a better answer.
Okay, thank you very much for a great talk, Matthew and Iain.